Okay, so I will be presenting the winning baseline solution for the text-guided challenge, which is BiomedParse. So just a brief overview of the overall model design. The BiomedParse model primarily follows the architecture of the SEAM model, which is the segment everything everywhere all at once. It includes four basic modular part, which includes an image encoder for encoding the input image, a text encoder for encoding the text prompt, a mask encoder for outputting the segmentation mask, and a meta object classifier for joint training of the image encoder and the object semantics. So for the actual implementation, the image encoder was initialized with focal, and the text encoder was actually a customized built transformer trained on the BiomedParse data, which is an image text mask triplets dataset the group created themselves. But they also kind of supports other like backbone plugins as well. So although the full fine-tuning pipeline of the code is not available, a part that specifically kind of stands out from their original training pipeline is I do want to highlight is the mixed dataset training methods. So basically, as you can see from the image on the right, this is their dataset, but it also happens into our challenge dataset as well. Especially for biomedical images, the datasets can be significantly imbalanced. So instead of just directly performing sampling, they did random mixing at the batch level during the training process. So basically what they did is they define a parameter PM called sampling probability with the equation I pasted here to control the training data's distribution from all datasets. So here the DM denotes the dataset for modality M, and the lambda could be any value ranging from 0 to 1. So using this equation in like to one extreme in cases of lambda equals 1, it will basically sampling datasets with a probability proportional to the dataset size. So in this case, each example from any dataset has the equal chance to be selected during the batch of the training. However, the training will also kind of be overwhelmed with huge datasets because the proportion is larger. On the other extreme, we can also set lambda to 0, and both these terms just reduce to 1. So in this case, each dataset has equal sampling probability, which gives us a good diversity of all tasks. But small datasets will be repeated, and there will be cases that large dataset potentially could not be exhausted because you are just sampling part of it. And so in order to balance these two extremes in their actual training implementation, they trained 20 epochs. So for the first 5 epochs, they set lambda equals 0.5. The next 10 epochs set it to 1, and the last 5 epochs set it to 0.5 again. And so moving forward to the inference pipeline, I will briefly go through their inference code and highlight some key implementation details. So as you can see, this is aligning with our test setting. The inference pipeline is processing one image at a time. And the beginning part of this code is basically loading the image and test from our MPZ format. Although in our cases, each sample would only contain one image and one target, but they do support where there could be multiple text prompts inputted for the same image, which kind of means that there are multiple organs or multiple targets in the same image. That's why you are seeing the separation token to separate different text prompts. And you could also notice that we do provide an instance label in the text prompt, but they are not used here. It's because BiomedParse treat all tests as semantic segmentation, and instance masks are obtained through post-processing only. So expanding on the image processing function, basically it's the code I pasted on the left-hand side. They do axis reordering to make sure that it will process on slides. The depth axis will always be the first one. And they did pad and resize, which is padding the image to a square. They set it to 512 and 512, and then resize it to 512 and 512. So after this processing, the image variable will have the dimension of the depths 512 and 512. And then they constructed the input tensor to the model, which they unsqueeze another dimension as the batch, which is basically one here because we're only processing one image at a time. Okay, so going a little bit deeper into the actual, like what the model actually does in its forward function. Here is basically the main difference between the 3D version of BiomedParse to the original implementation in their Nature paper. Because the original model was a 2D model, and the only way they do 3D, they could process this 3D image is they do a slice by slice. But here for our challenge, they specifically adapt their 2D model into like a 2.5D version to handle the 3D volumes. So here the this if clause is when the image is actually 2D. So as our images are 3D, we directly go to here. What it does is basically samples a previous light channel and the previous slide light channel and the next slice light channel and concatenate them together. So for image one, it creates the slice at index one and then concatenated by all the slices until the last one. So here I kind of write down a few examples as it's probably more intuitive. So image one, you have slice one and followed by slice zero all the way to the last, the second last slice. And then for image two, it starts from slice one and goes all the way to the last slide and then duplicate the second last slides. Sorry, this should be D-1 because it's the last one. So, and then after concatenate all three of them together and do the transpose, what it does is basically it converts a single channel 3D volume into a series of 3D channel inputs for the 2D models to process. So each 2D slice here, it's in which is basically the original slice accompanied by its adjacent slice, which is the previous one and the next one. So each of the slice on the depth axis right now is a 3D channel image, and it could just ready be processed individually into the 2D models. So after the image processing, here is the part they use to generate the text embeddings. So they do support multi-prompt process for multi-prompts, but again, here we are only having one prompt for the image. This function is not used here, but I do expand on their text token embedding function. They use the clip tokenizer and selects the classification token for each sample and projects both the class and the token embeddings into the shared space and returns the results obtained by the tokenizer. So after getting the text embeddings, this part of the code is where they mask out the tokens using the attention mask and then filters out the empty embeddings and then construct everything into a dictionary as the output of the encode prompts function. And then with the text features and the process image obtained, we go back to the forward pass. We feed all of them into the forward function. So the pipeline basically iterates through the volumes we obtained earlier over all slices. And the slice batch size variable is set to 4, which means it will process 4 slices in the 2.5D volumes at a time. it will get the image embedding first from the backbone, and as all the slices already will have the same prompt, it the next couple lines, sorry, the cursor's here. The next couple lines here will try to match the batch size of the prompt with the actual size of the image, and batch size of the image. So P here is just the number of prompts. It's equals to 1 of all the times in our case. And with both the image and text features as input to the predictors, the prediction outputs will be obtained. And the predictions are then saved into variables, this variables, by concatenating the results through every iteration. So this part of the code is within the while loop from the previous screenshot. Will concatenate every batch, and the final results would be obtained here. And they did a reshape and then return the predictions. So after that, they resized the raw prediction output back to 512 and 512 and applies post-processing, which basically is a non-maximum suppression function to filter out the overlapping masks with low confidence. And then this function is to merge a list of boundary masks into a single multi-class mask. But again, as in our test cases, we only have one target per case. This is like kind of redundant, but it will be useful when there's multiple class in one image. Lastly, the process output function is basically the reverse of process input. It reprocess the results back into the 3D prediction volume, which is basically resizing it back by removing the padding and restore the axis order. And then the obtained final prediction is saved in the MPZ format as our challenge expected. So finally, as a recap to the highlights of the BiomedParse implementation, some things I find truly kind of insightful is that they use the mixed dataset training strategy to account for modality imbalance, which is kind of really prevalent in the biomedical image analysis field. And they used a 2.5D design to handle 3D image input with a 2D model. And finally, they applied the non-maximum suppression to avoid duplicate predictions for the same targets. And that concludes my presentation.